Hello and welcome back. I am Divya. This is For the Love of Physics, and today we are going to discuss probably the most important problem in quantum mechanics, or at least I should say the most famous problem in quantum mechanics. So this is the infinite square well potential problem, or infinite rectangular well potential problem, or particle in a box problem, whatever you want to call it. It's a very ideal problem. By studying this problem, we can get accustomed to, or we can familiarize ourselves with the framework of the quantum mechanical theory, how to go about solving the Schrodinger equation and how to go about interpreting its solutions and the associated probability densities and other physical quantities. It basically gives us a quick preview of everything that is happening in quantum mechanical theory. So here we have a particle in a very classical manner I'm explaining right now, which is stuck between two walls. So let's suppose we are dealing with a 1D motion. The particle can only move along the x-axis, but there are these unbreakable, impenetrable walls at x is equal to 0 and x is equal to a. So the particle is stuck in between. The particle is free more or less in this region, but it cannot go beyond it because there is some kind of an infinite force that prevents the particle from going beyond x is equal to a and in the negative axis beyond x is equal to 0. This is the classic problem. So I'm going to basically solve the Schrodinger equation, obtain the solutions, look at the nature of the solutions, obtain the probability densities, look at the discrete energy levels, and then look at the properties of these bound states. So let's start. We're going to start with the time-independent Schrodinger equation, all right, which is the very common minus h cross square upon 2m d2 psi upon dx2 plus v psi is equal to e psi. This is a time independent Schrodinger equation. Now we can divide this entire region into three regions. Let's suppose this is region number 1, region number 2 and region number 3. Now based on the definition of the problem itself, because the particle cannot penetrate these infinite potential barriers, the particle can never exist beyond x is equal to 0 and x is equal to a. That means the wave function by definition in the region beyond x is equal to 0 is 0 and beyond x is equal to a is 0. And the particle has no probability of existing, let's suppose, in region number 1 and here region number 3. Okay, the particle only exists in region number 2. So therefore, we are only going to solve the Schrodinger equation for the region number 2. But the interesting thing about the region number 2 is that the potential here is 0. So inside the particle is behaving like a free particle. So that means for region number 2, if I say I'm only solving the Schrodinger equation for region number 2, the potential here is 0, which simplifies our differential equation because now I have minus h cross square upon 2m d2 psi upon dx2 is equal to e psi, and then we have d2 psi upon dx2 minus is equal to 2me upon h cross square psi, and finally we get d2 psi upon dx2 plus 2me upon h cross square psi is equal to 0. This is a second order ordinary differential equation. However, this particular term here, 2me upon h cross square, what does it actually mean? If you look at the energy of the particle, then inside, because the potential is 0 here, it is nothing but p square upon 2m. So that means p square is equal to 2me, e being the kinetic energy here. But what is p? We know from the de Broglie hypothesis that p is nothing but h cross k, all right, k being the wave number. So this comes out to be p square. So this is h cross k square is equal to 2me, right? So this essentially comes out to be k square is equal to 2me upon h cross square. So 2me upon h cross square is nothing but k square. So finally I can write the differential equation as d2 psi upon dx2 plus k square psi is equal to 0, where k is basically the wave number associated with whatever the wave mechanical solution of the Schrodinger equation is for this particular particle, and that is related to momentum or the energy in this particular fashion. So this is the differential equation. Now the solution of this differential equation is actually very simple, because this is a very standard differential equation that has oscillatory solutions. So the most general solution can be written as psi x is equal to something like some kind of a constant, let's suppose a dash e to the power iota kx plus b dash e to the power minus iota kx, something like this. So the most general standard mathematical solution for a differential equation like this. Now, what is e to the power iota something? We can always decompose e to the power iota something in terms of sines and cosines, right? So if I have something like e to the power iota theta, that can be written as like cos theta plus iota sine theta. So that means e to the power iota something can always be decomposed into cosines and sines. So if I do that here and sort of combine whatever constants arise from it, even absorb the iota here, this can be simply written as psi x is equal to, I will have different constants now. Let's suppose I take a sine kx plus b cos kx. All right. So for a particle which is stuck in an infinite potential well, a rectangular potential well, the solution is an oscillatory solution, as simple as that. However, we can further simplify this solution by applying boundary conditions, because this is ultimately a bound state. The answers that we are going to get are bound states because the particle is bound here, and we can apply the boundary conditions here. What are the boundary conditions? By definition of this problem, the wave function at x is equal to 0 and at x is equal to 0 and at x is equal to a is 0, because that is where the particle stops. The wave function becomes 0. There is a continuity, let's suppose, of the wave function as well as its derivatives at these locations. However, the derivatives themselves at these locations also is equal to 0. So if I apply boundary conditions, then I can further simplify this whole thing. All right. So let's say boundary conditions. All right. I'm going to rub the right hand side part. I hope you have written this down. Okay. So the first boundary condition is that the wave function, and I'm calling it wave function, but it is actually the eigenfunction, all right? I have spoken about this in one of my previous lectures, that when we are solving the time-independent Schrodinger equation, we end up getting the eigenfunction. The wave function is essentially the eigenfunction times the time-dependent part. But sometimes we refer to both of them using the same word, the wave function, but we need to be careful that technically it is the eigenfunction or the eigenstate of this particular system. So this eigenstate at x is equal to 0 is 0, because if this is 0, the wave function comes out to be 0 at x is equal to 0, because here the potential is infinite. All right. So if I apply this particular expression here, this simply becomes a sine k times 0 is 0 plus b cos k times 0 is 0 is equal to 0. Now sine 0 is 0, right? So we are left with cos 0 is equal to 1. So we are left with b is equal to 0. That means this particular constant b is 0. That means we can simplify this further as saying that psi x is equal to a sine kx. Now this is a much more simpler state, the functional expression, okay, for this particular system, a being the normalization constant. I'm going to find that out in a moment. But before I do that, I want to show one more thing. Here, if I apply another boundary condition, also if I say that psi at x is equal to a is also 0, right? Because here also the potential is infinite, then I end up getting a sine Ka is equal to 0, which simply means that sine Ka is equal to 0. Now when sine theta is equal to 0, it is only true for certain values of the theta, right? Theta 0, theta 180 degrees, theta 360 degrees, and on and on. So it simply means that Ka is equal to n pi. Okay, I should include plus minus also, but I'm not including it here because it's not going to make any difference. So n is equal, so 0, pi, 2 pi, 3 pi, 4 pi, for all these values, sine that particular angle is going to be 0. But we can't really include pi here, n is equal to 0 here, because the moment I say n is equal to 0, I will actually end up getting a vanishing wave function. So therefore, we will only include values for n is equal to 1, 2, 3, 4, the integers basically, or I should say the natural numbers here. So now let's further see what else we can deduce from here. So k square a square is equal to n square pi square. But what is k square? K square is equal to 2me upon h cross square, right? So if I substitute that here, I should get 2 m e upon h cross square. A square is equal to n square pi square. Now if I write it properly, I should get an expression for the energy. E is equal to n square pi square h cross square upon 2ma square. This is the energy of the particle, the total energy of the particle in this particular system. However, n can take values of 1, 2, 3, 4 and on and on. That means there are a large number of energy values. These are known as the energy eigenvalues of the system, I should say En, or the energy levels associated with this particular system. First of all, in a classical system, if we had a classical system like this, where a particle is stuck between two walls, the particle could be at rest, particle could be moving with a certain velocity, bouncing back and forth, and the velocity can be anything. It can be a low velocity, a very high velocity. So therefore, there is no restriction on the particle's energy levels or the energy itself. It's a continuous distribution of energy for the particle in a classical system. But the moment we go from a classical to a quantum mechanical system, the first thing that we realize here is that the energies which are allowed for the particle to have by the Schrodinger equation are discrete energy levels. This is one of the important features of the quantum mechanical theory, that even though we have a particle which is bound in a system, because of the boundary conditions and the nature of the quantum mechanical theory, the particle can only exist in certain allowed energy levels, and it will never be found with energies which are in between these energy levels, if that makes sense. So that means if a particle is in an infinite potential well, the particle will have energies which are allowed, having values let's suppose I call this E1, this I call E2, this I call E3, this I call E4 and on and on. So let's imagine that this is the energy axis, and for a classical system, the energy axis, any value is possible, because in classical systems, the particle can have any value of energy out there. The theory doesn't restrict the particle from having a particular energy. However, in the quantum mechanical system, if a particle is stuck in an infinite square well potential, the particle can be in an energy level E1, where E1 is equal to, n is equal to 1 pi square h cross square upon 2ma square. This is one value of energy, the lowest out of all of them. So this is also known as the ground state energy level. For n is equal to 2, I have E2, where E2 is simply equal to 2 times 2, 4 pi square h cross square upon 2ma square. Similarly, for n is equal to 3, I have E3, where E3 is equal to 9 pi square h cross square upon 2ma square, and on. For n is equal to 4, we have E4. E4 is going to be 16 pi square h cross square upon 2ma square. So that means a particle cannot have, it's not allowed to have any energy between these levels. Okay, the particle cannot have an energy between these levels. Think of this as an energy axis. The particle cannot have energies in between these levels. The particle can only be having energy either E1, this value, or E2, this value, or E3, this value, or E4, this value, like that. So these are discrete energy levels that the particle can possess, which is a very important feature of a quantum mechanical system. I can also simply write this as En is equal to E1 is pi square h cross square upon 2ma square times n square. So I can write this as n square E1, where E1 is the ground state energy. And n here can take the values of 1, 2, 3 and on and on. Alright. It cannot take the value of 0. I will show you why it cannot in just a moment. And the momentum that is associated with these energy levels is essentially equal to h cross k, right? Because that's what momentum is. And k is equal to n pi upon a. So I should have h cross nh cross pi upon a. For particles going forward or backward, I will have plus minus sign here. Alright, so these are the momentum associated with these energy levels. Now, I have this eigenstate solution, but here A is unknown to us. So to find out A, I must normalize this. So you know from the Born statistical interpretation that the probability of the particle being found in the entire universe, or in this case from 0 to A, is always equal to 1. Right? So by imposing that condition, I can find out the value of A. So let's find that out first. For that, I'm going to rub this. I hope you have written all of this down. Let me just rub this part. So this is basically the condition of normalization, all right, to find out the constant associated with the eigenfunction solution, which is to impose that if I try to find out the probability corresponding to this state between minus infinity and plus infinity, it should always come out to be equal to 1. So if I put our solution here, this is simply going to give me from minus infinity to plus infinity a sine kx times a sine kx. So this should be a mod square sine square kx dx is equal to 1. I don't yet know what a is. Is it real or complex? It turns out to be real, but let me show it to you. And because the integration is from minus infinity to plus infinity, but the particle cannot exist beyond x is equal to a and x is equal to 0. So the integrals for those regions anyways comes out to be 0. So I am only concerned with the integration from 0 to a mod square sine square kx. What is sine square something? Sine square something can be written as half of from 0 to a 1 minus cos 2kx, right? This is a trigonometric identity. So cos 2 theta is equal to 1 minus twice sine square theta. So sine square theta is equal to 1 minus cos 2 theta times half. Okay, so if I integrate this, I should be able to get a value of a. So this becomes half of a square. So now this is simply an integration from 0 to a of dx, and this is an integration from 0 to a of cos 2kx dx equals 1. This becomes half a square. This is ax, which comes out to be a, minus this is 1 upon sine 2kx in the limits of 0 and a equals 1. Now what is sine What is k? K, we found out just a few moments back that k was equal to n pi upon a, right? So it should be kn, so k n pi upon a. So if I write here n pi upon a, so this comes out to be 2 n pi x upon a. So instead of 2kx, I have 2n pi x upon a. So for x is equal to a, I have 2n pi, where n can take the values of 1, 2, 3, 4 like that. So sine that is 0, right? And again sine 0 is 0. So this essentially the whole thing turns out to be 0, and we are left with, okay, let's go here. We are left with half a square times small a is equal to 1. Now here I should find out a, right? Now because you can see the a mod square times small a is equal to 1, so a should be a real number. Then we will actually get a is equal to 2 upon a root over. This is the normalization constant. So if I combine the eigenfunction solution with the normalization constant, finally we will get a couple of solutions. So the eigenfunction or the eigenstate solutions look like root over 2 upon a sine kx. So k is n pi. So this is essentially n pi x upon a. And if I write the wave function solution, I simply need to multiply this with e to the power minus iota omega t. Do I have the space for that? I think I should write it here itself. Okay, let me write it here itself. So the wave function, which is a function of both x and t, is equal to root over 2 upon a sine n pi x upon a times e to the power minus iota omega t. That's it. There you have it. Now, of course, omega here can be written in terms of energy. Omega is equal to E upon h cross, where E is this. So I can, yeah, you can write it here also. You can apply E in this particular expression because omega actually is En upon h cross. All right, I'll just keep it here. So these are the eigenfunction solutions of the infinite square wave problem, and these are the wave function solutions of the infinite square wave potential problem. As you can see, because n can take the values of 1, 2, 3, 4 and on, you end up getting an infinite number of solutions. Now also, it must be clear from here why n cannot be 0. If n was 0, then this will be sine 0 and the wave function will ultimately vanish, which means the particle doesn't really exist, which is not really allowed, right? Therefore, n can only take values of 1, 2, 3, 4 and on. So you have infinite wave function solutions for this particular problem, and all of these wave function solutions correspond to these distinct energy levels. That means for psi 1, the particle is in energy level E1, for psi 2, the particle is in energy level E2 and on. So I should write here as psi n. All right. Now, fortunately, the eigenfunction solutions are real, so I can actually draw them and see how it looks like. So let me do that by rubbing a part of the board. So I hope you have noted everything down. Let me rub this portion of the board. So we have obtained the eigenfunction solutions, the wave function solutions, and of course the energy levels for this particular system. So the particle in the infinite square wave potential can only exist in these energy levels, and these energy levels are all associated with their respective eigenfunction solutions. So that means for a particle existing in energy level E1, it will have a eigenfunction psi 1, which is equal to 2 upon a sine pi x upon a, right? N is equal to 1 in this case. So how does it look like? Well, a wave function like that between x is equal to 0 and x is equal to a will look something like this. Half of a sine wave essentially. And for a particle in energy level E2, will have an eigenfunction solution psi2 is equal to root over 2 upon a sine 2 pi x upon a. 2 pi x upon a. Should I use a different color for this? Let me use a different color for this, okay? I'm going to use orange, or maybe I have another color. No, this is fine. So for here, I have sine 2 pi x upon a between 0 and a looks something like this, one full sine wave. For a particle in energy level E3, I'm going to have psi 3 is equal to root over 2 upon a sine 3 pi x upon a, which is going to look like something like this. Okay, and again it keeps on going on and on and on. For let's suppose psi 4, which is root over 2 upon a sine 4 pi x upon a, our eigenfunction would look like this. Do you see that? So you keep getting an infinite number of eigenfunction solutions, each of them corresponding to a distinct energy level for the particle. So if the particle is in any one of these states, it will have an energy corresponding to that only. Now, what is interesting is that if I try to find out other information from these eigenstates, once we obtain the Schrodinger equation and these eigenstate solutions, there are other kinds of physical quantities that we can look at. The first thing is the probability density, right? In quantum mechanics, once we have a solution, we are interested in looking at the probability density of the particle. So each of these states will have a corresponding probability density. Now, first of all of these states are stationary states. So if you look at the wave function, if you take its probability is what? Psi mod square. Because there is this term here e to the power minus iota e t upon h cross, in the psi mod square, this term will vanish. And you will only be left with something like 2 upon a sine square n pi x upon a, which is essentially a function that is only dependent upon like x. So it is constant in time. So the probabilities of these eigenstates are constant in time. They represent stationary states. And because a probability is essentially going to represent something like, let's suppose probability is equal to psi n xt mod square is going to be equal to 2 upon a sine square n pi x upon a. The other term is going to vanish because if you take the complex conjugate, it will get cancelled out. I can draw these functions here also. So probability is anyways positive, so I won't have these negative oscillations. So it will look something like, let me draw with the white one, okay? It will look something, or maybe irrespective colors, it will look something like this. This is the probability density of the particle when it is in the ground state. What about the first excited state? The probability density of the particle when it is in the first excited state is this. The probability density of the particle when it is in the, I think I should use the same colors, it is in the second excited state is this. And the probability density for the particle when it is in the first, second, third excited state is this. You see this? Now what does it mean? It means that the particle has a certain probability of being found even within this well, right? The particle isn't likely to be found at all the places within the well with equal likelihood. No. Even within this well, there are certain regions in which the particle is more likely to be found, and that depends upon its eigenstate solution. So for different kinds of eigenstates, if I make a large number of measurements on similar systems, the particle is much more likely to be found in specific areas for corresponding to that particular state itself, right? So this is very interesting, isn't it? Now, to complete this video, I want to discuss some properties of these eigenstates and their probability densities one by one. So let's do that. So let us look at the properties of these eigenfunction and wave function solutions. And these are interesting properties. All right. First of all, it is clear that we have infinite eigenfunction solutions. N can go from 1 up to infinity, and their corresponding energy levels are also infinite. So we have infinite eigenfunctions and energy levels, discrete energy levels. Okay. Now, if you go from n is equal to 1, 2, 3 and on, you see something interesting in the physical representation of the eigenfunctions, that if you ignore the boundary points, okay, the eigenfunction has to go to 0 at the boundaries, that is x is equal to 0 and x is equal to a, because at the boundaries the potential is infinite, the eigenfunction has to go to 0, right? But if you ignore these, with every increment in n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, there is an increase in the nodal points. What are nodal points? You see these points, this point. This is a point in which the probability of the particle being found is 0, which is kind of interesting. You see that the particle exists within the well, but except for the ground state, for all other states, there are certain points in this well where the probability of the particle being found is absolutely 0, which is kind of very interesting, isn't it? So for the first excited state, there is 1 point. For the second excited state, there are 2 points. For the third excited state, 1, 2, 3, there are 3 points. So if you look at, and these points are known as nodal points. Okay, so nodal points are those points corresponding to which the particle has a 0 probability of being found there. So if we look at psi 1, how many nodal points does psi 1 have? 0. If we look at psi 2, how many nodal points does psi 2 have? 1. If we look at psi 3, how many nodal points does psi 3 have? 2. If we look at psi 4, how many nodal points psi 4 has? 3, and on. So if you take any kind of an eigenstate, it has n minus 1 nodal points. That means there are n minus 1 points for every eigenstate solution for which the particle's probability of being found there is exactly 0, which is kind of very interesting, isn't it? And also, if you look at the nature of these eigenfunctions, they have alternating even and odd parity with respect to the center of the well. Now you see the infinite square well that we have chosen is a very special case in the sense that it is asymmetric. Okay. Asymmetric. So there are 2 cases that we usually study. One is a symmetric case in which the infinite square well can be between minus a by 2 to plus a by 2. So essentially the potential well is centered with respect to x is equal to 0. However, we did not choose that case. We chose the asymmetric case where the well goes from 0 to a. So it is centered at x is equal to a by 2. But let's imagine, because it's not going to change the eigenfunction solutions if we just shift the well. All right. If I shift the well, it's not going to change the eigenfunction solutions. So if I compare these solutions with respect to the center of the well, it is clear that they have definite parity. So this has even parity, this has odd parity, this is even parity, this is odd parity, and on. So with respect to the center of the well, okay, I'm saying with respect to the center of the well, so this is point number 3, which is very important, with respect to center of well. The eigenfunction solutions have definite parity and alternate parity, essentially. They alternate. So that means psi 1 is even, right? Psi 2 is odd. Psi 3 is even, and on. Sorry, yeah. And even, odd, even, odd, even, odd, it keeps going on. Again, I have to be very clear with respect to the center of the well. So if it was centered at x is equal to 0, then this is an even function, this is an odd function, even function, odd function, and on and on. Now there is another property that these eigenfunctions share, and that is the property of orthogonality. Okay, I have discussed orthogonality in one of my previous videos. Orthogonality simply means that these solutions are independent of one another. So if I take, let's suppose I take psi1 and I do its inner product with, let's suppose, psi2, it will come out to be 0. You can try it out. Take it as a homework problem. You can take psi1, psi2, integrate between minus infinity to plus infinity with respect to x, you should get 0. So in general, psi m star psi n dx integrated between 0 and infinity comes out to be 0 if m is not equal to n. If it is equal, then we end up getting the normalization condition. Otherwise, it comes out to be 0, which simply means that distinct states are independent of one another. They are orthogonal with respect to each other, which simply means that they are independent of one another. And finally, the general wave function solution of this particular system is nothing but psi xt is equal to the eigenfunction solution, first of all, root over 2 upon a sine n pi x upon a e to the power minus iota ent upon h cross, where en is the energy levels. And then if I do a linear superposition of all of them with coefficients, let's suppose Cn, linear superpositions with respect to n is equal to 1 to infinity, this gives us the general solution of this particular problem. Every state has a probability associated with it. If I make a measurement, whether the particle will be found in a given state is given by Cn square. Okay, the probability that a particle will be in a certain energy level is given by Cn square. I hope you can see this. All right. So as you can see, this is the beautiful problem of the infinite square well potential and the quantum mechanical description of it. A classical problem is very simple, particle bouncing back and forth between two extremely rigid walls. But in quantum mechanics, you have these very unique, interesting features that the particle can only exist in definite energy levels, separated in this particular manner according to this particular expression. The eigenfunctions and their probability densities look something like this. So the particle cannot exist everywhere with equal likelihood. For every single state, the particle has a certain likelihood of being found in some region or the other, and all these interesting features. So I hope you enjoyed this video, this lecture, because this is a very interesting problem. And let me tell you something, this is very important also with respect to interviews. So if you go into an interview and you say to the panel, I love quantum mechanics, then it's very likely they might ask you a question regarding this particular problem. So I hope you will be able to face those interviews after having watched this particular video. I am 𝑑𝑉𝑒𝑠 and this is For the Love of Physics. Thank you so much. Take care. I will see you in the next video. Bye-bye.